Hello, everyone, and thank you for being here. My name is Xiangyu, and today I will be presenting our research titled A Reinforcement Learning Framework for Real-Time Update of MPC Parameters with Ensured Stability. Let's start with a brief background on Model Predictive Control, or MPC. MPC is a highly effective established technique used to control multivariable systems subject to constraints. At its core, MPC uses an internal dynamic model to predict the future behavior of a system over a finite time window, known as the prediction horizon. By solving the optimization problem at each time step, it calculates the optimal control screens to track a reference trajectory while strictly respecting system constraints. So here is our motivation and task. While MPC is powerful, its practical performance highly depends on the accurate tuning of its parameters, specifically the prediction horizon NP and the cost function weighting matrix Q and R. Currently, users usually rely on manual trial and error tuning. Not only this method is super time consuming, but the resulting performance is often inconsistent. Because the parameters are fixed, the controller's performance easily degrades when the system operates under dynamically changing environment conditions, as it simply cannot adapt. To address this, we turn to reinforcement learning. Reinforcement learning (RL) has shown a great ability to solve complex sequential decision-making problems. As you can see in the typical RL loop on the slides, an agent interacts with an environment, takes actions, and receives a state and reward signal. It learns a policy to maximize its long-term cumulative reward. Our goal is to leverage an RL agent to continuously and simultaneously adapt the parameter of MPC to maximize both tracking performance and control efficiency. To apply RL, we formulate the parameter adaptation process as an MDP. Our environment is a closed-loop system consisting of the MPC and the plant. You can see the green area in the slide. The state space gives the agent an operational snapshot, specifically the tracking error and the previous control input. The action space allows the agent to select the tuning parameters. We usually normalize R and to isolate the state penalty Q and the prediction horizon NP as the primary drivers of the system's aggressiveness and foresight. Finally, our reward function is a tiered structure that penalizes high tracking errors and excessive control effort, guiding the agent toward the better efficiency. However, introducing dynamic parameter updates create a critical theoretical challenge. It fundamentally transforms the closed-loop architecture into a switched system. In hybrid control theory, it is well known that the arbitrary switching between individual stable configurations can cause transistor energy to accumulate, which can completely destabilize the overall system. Traditionally, researchers use dwell time constraints to force the system to hold a parameter set for a minimal period of the time. But this is a conservative approach that restricts the controller agility and responsiveness to sudden disturbance. Our key insight to overcome this is to completely decouple the performance-driven policy search handled by the RL agent from the strict stability verification. Because changing the horizon or state width naturally changing the numerical value of the MPC cost function. And instead, our framework enforces a strict monotonic decay across a single time invariant energy metric using a common Lyapunov function. This acts as a static ruler to guarantee stability. Then this leads to our proposed solution. So you can see here is our proposed framework, which is a stability first RLMPC framework. At the high level, the RL agent can interact with the environment, observing the states and proposing the tuning parameters. At the lower level, a two-stage safety mechanism bridges the RL agent and the MPC. We use an offline certification step to create a safe action space. Then, an online stability filters act as a real-time safety gate. Let's look at how these two stages work. First is the offline certification outlined in the algorithm 1. Before the system even goes online, we systematically evaluate candidate parameter sets across a discrete grid covering our state space constraints. We verify that each parameter combination yields a contracting cost trajectory over the domain. By doing this, we actively construct a stability guaranteed action space. The RL agent is only allowed to select the actions from the pre-certified library. Next, we establish our static ruler for the online filter. At the start of the operation, we compute static reference matrix PREF using the backward RDE based on the initial parameter choice. This matrix precisely characterizes the baseline energy required to drive the state to the orange under linear feedback. Because the PREF remains completely fixed, it allows us to objectively measure convergency to the orange entirely independently of the dynamic parameter and when of the RL agent is proposing. Finally, we implement the real-time stability filter shown in algorithm 2. At every time step, the RL agent proposes a new parameter update. Before the update is applied, the stability filter calculates if the resulting control input induces a strict decay in our static reference energy metric. If the metric decays, the parameters update. If it fails the check, the filter rejects the RL agent's proposal, securely defaults to the previously known safe parameters. This permits the arbitrary switching speeds while strictly guarantees the stability. To validate our framework, we conducted a simple numerical evaluation comparing three RL algorithms, which is the DQN, PPO, and TRPO. Since we utilize a discrete pre-certified action space, value-based methods like DQN are well suited here. As you can see in the training progress graphs, the DQN agent achieved the highest final episode reward of 420, and its estimated returns accurately tracked the observed rewards. While the PPO and TRPO are very capable algorithms, In this specific example, they are worse than the DQN. And so consequently for our uh, framework, DQN proved the most reliable and suitable choice. And in the figure 2, you can see here is our stability and feasibility analysis for our simulation example. We can find the safe bound for the prediction horizon NP and for the matrix QR as well. Oh, looking at the physical tracking performance on the left, the DQN tuning controller demonstrated very good transist and steady state tracking accuracy, outperforming both the TRPO agent and traditional static MPC baseline. More importantly, you can look at the middle column plotting the RIL parameters. The markers show that a very high overlap between the RL agent proposal parameter with stability guaranteed parameters. This proves that the agent successfully learned a natively stable policy operating safely within the stability guaranteed region with a filter, which can perfectly catching any unsafe deviations. In conclusion, this paper introduced a novel framework that integrates reinforcement learning to dynamically tune MPC parameters, specifically the weighting matrix and the prediction horizon in real time. To address the critical challenge of ensuring closed-loop stability during this arbitrary switching sequence, we developed a two-stage safety mechanism. First, we construct a pre-certified stability guaranteed parameter set offline. Then, we applied a real-time supervisory stability filter based on a common Lyapunov function, acting as a safety gate that can enforce strict energy decay regardless of the RL agent's exploration. Our evaluation demonstrated DQN agent better than PPO and TRPO and the traditional MPC baselines. So for the future work, we plan to extend this framework to nonlinear systems and deploy it onto physical autonomous platforms such as the code router setup as pictured here, and also the autonomous surface vehicles as well. Thank you all for your attention and time today. I would be happy to answer any questions you might have. Please feel free to leave your questions and comments there.